Hello. Alright, so I am outside of my house this time, which is different, but it's nice outside. So, we have been talking about thermodynamics, and the next part of this, so we used calorimetry, and we just kind of sort of talked about delta H, the enthalpy. And now we're going to talk about how to get delta H using Hess Law, it seems really weird, but it's easier when you really get the hang of it. So, if a reaction is carried out in a series of steps, so if it's not just like one single reaction, then the overall change in enthalpy will be equal to the sum of the enthalpy changes for the individual steps. So add them up. That's it. The overall change will be the same if a reaction is carried out in one step or in several steps. So if it is in one step or if the same reaction is in several steps, the overall change in enthalpy, energy, heat, whatever you want to call it, is going to be the same no matter what. So if we look at an example, sorry, I'm like wobbly. If we look at an example for Hess's Law, we see it's asking us to calculate delta H for a combustion of methane, CH4. So let's see here. So CH4 plus O2 yields CO2 plus H2O, and we have like this weird set of three reactions down here with delta H's associated with them. So it says step 1 down here. Step 1, CH4 must appear on the reactant side. So our CH4 is over here. So we need to reverse number 1 so that CH4 is on the left-hand side of the arrow. So before I even read step 1, I saw that in these three reactions that I have right here, CH4 is only mentioned right here, which means it's the only one that will work for that particular reactant. So because I need it on the reactant side, all I do is basically just flip this reaction, and if I'm going to flip that reaction to get CH4 on the reactant side, I just change this delta H value to be positive, or negative if it was already positive. In this case, it'll be positive. So you'll see right here, they made it a positive 74.8. Next step, it says down here, step 2, keep reaction number 2 unchanged because CO2 belongs on the product side. So CO2 is right here on the products, CO2 is right here in the products. We just leave that as it is, and we add that negative 393.5 to our existing positive 74.8. And then step 3, multiply reaction number 3 by 2. So if we see here, we have H2 plus 1/2 of O2 yields H2O, but I have 2 O2 right here and 2 H2O over here. So basically, I'm just looking at the H2O in this case, because I'm just looking at whatever's in my reaction, like as I go. And so I need to multiply this H2O by 2 to get 2 H2O, so I just multiply this by 2 to get that, and then I just add them all up to get my answer. Alright, so now we're going into another example problem. I do not have a calculator on me, so we're going to do this in more of a logistical sense. So it says, example number 1, calculate delta H for the following reaction using the information in the table below. So our reaction is 4NO2 plus O2 yields 2N2O5. I'm first going to look at, do I see NO2 anywhere in these bottom reactions? And I do. It's right here. But it's 2NO2, which means I need to multiply this by 2 in addition to flipping it to a positive because this needs to be on the reactant side. So I multiply this by 2 and I flip it to a positive number. Next, I'm going to ignore the O2 and just go straight to this N2O5 because I only have 2 reactions here, so there's really only 2 things I can do. So N2O5 is on the correct side, but again, I need to multiply it by 2 because in this equation it is multiplied by 2, but in this one it is not. So I just multiply this number by 2, and then I add those two numbers up that I got. And then that will be your delta H for the entire reaction. Another example, calculate delta H for the reaction of 3C plus 4H2 yields C3H8. Using the information below. So what I see is 3C right here, and I see 1C right here. So it's on the right side. I just need to multiply this number by 3. So 3 times negative 3, 93.5. That is like ugly, but whatever. Plus 4H2. I see 2H2 right here. Multiply this by 2. Multiply this number by 2. It's on the right side, so that's good. So 2 times negative 571.7 plus, and then C3H8. I see that right here. So all I need to do is flip this number to be positive. I just add 222 point whatever that is. Add all those up to get your delta H for the reaction, and then you'll be done. Really, really simple. So just make sure that your reactants are on one side, products on the other. Add up those numbers, making sure that your signs are correct and the numbers for the coefficients are right. Alright, so the next method for us to find delta H is using enthalpies of formation. Enthalpies of formation, standard enthalpy of formation, is just this hypothetical value that indicates how much heat would be lost or gained during the formation of 1 mole of a compound. The only difference in this versus anything we've already done is the fact that this is going to be 1 mole of the compound and it's at standard state, so 25 C and 1 ATM. And that weird little O superscript is the standard part of that. Dog. Hello, dog. Hello. Hey, buddy. Alright. So, standard enthalpy of formation for methanol. So we're looking at this. C plus 2H2 plus 1/2 O2 yields CH3OH. The standard enthalpy of formation for that reaction is negative 201 kilojoules per mole. Heat of formation reactions are always written so that all reactants exist as they would under standard conditions, and there is 1 mole of product. So for anything that we're going to have a delta H for formation, we're also going to have 1 mole of this product, and our reactants are written as they would be by themselves existing in standard conditions. So we can see here there's a bunch of standard enthalpy of formation values for elements in their most stable form, and it's all 0. So anything for an element in its most stable form, so O2 is, so any diatomic is going to have something 2, N2H2Cl2, and then like any element that's just sitting by itself, all of their delta H values, standard values of formation, are all 0. And we can use that in our examples. So basically, same kind of reaction we've always seen. The formula for calculating this standard enthalpy of formation of the reaction is going to be equal to the sum of the change in the enthalpy for the products minus the change in the enthalpy of the reactants. The only thing that's different is the fact that we multiply it by the coefficients. Each one we multiply by their coefficients, which isn't that hard to do. So, looking at an example, find delta H, the standard enthalpy of formation for the reaction for a thermite reaction under standard conditions. So it's the reactants, right? Products minus the reactants. So this will be 0, and this will be 0. But these two will have numbers associated with them. So it's going to be the products minus the reactants, so it'll be delta H, standard reaction, whatever, equals, there's no coefficient in front of here, so it's just 1 times the delta H of formation. I don't know what it is for that. Sorry, this is super ugly because my dog ate the pen that I was using. So I have to figure that out. I'm just going to talk. So it's going to be, so this is 0 and this is 0 because they're at the standard, like, existing state. This will be a number multiplied by 1, subtracted from this, multiplied by 1 as well. And that will get you the delta H for the reaction. Same goes for this one. I don't have values in front of me, but it will give you values. So this will be 0 because it's just O2. Everything else will have a number associated with it. So we will do products minus reactants. So we'll do 2 times H2O's value plus, because it's the sum of the products, 2 times SO2's value for the delta H of the reaction, subtracted from 2 times the value for that H2S. And then it'll give you the values for that, and you just calculate it, and you will get your delta H for the standard of the reaction. And that'll be it. So next time we'll be talking about entropy, which is exciting and fun, trust me. So I'll see you then.